So, good morning, students. We are moving towards the laboratory exercises for third year or fifth semester. So, in the process, we're going to use digital storage oscilloscope for the analysis of or measuring of communication signals. Whatever the experiment we are going to deal with, we are going to use digital storage oscilloscope. And you all guys are very familiar with the cathode ray oscilloscope or simply CRO. And and you know how to operate with the CRO. And DSO is going to be operated with the same manner, but some advancements when compared to CRO. So this video presents the usage of DSO and how it can be utilized for measurement of communication signals, and what are the options and what are the facilities that are available when compared to CRO is going to be discussed in this video. Okay. So now we'll start with a small presentation. So here we know that oscilloscope is an instrument which is used to measure voltage waveform with respect to time, right? So it is a uh, optical device, or you can see optically the signals, right? So you have a sinusoidal signal or any other signal, whatever we encounter during our laboratory classes, we have seen physically or optically uh, uh, in order to measure the voltage, time, and from time we can measure frequency, and even to a certain extent we can measure the rise time, fall time, etc. Okay, and this oscilloscope can also be called as an XY plotter. So in the x-axis it is going to plot voltage, and in the y-axis it's going to in y-axis it's going to be the voltage, and x-axis is going to be the time. So it goes to plot voltage versus time. So it is a time domain display of a signal. And this oscilloscope normally requires manual interpretation for measuring the readings, right? If you remember, in our laboratory classes for electron devices or electronic circuits laboratory, you would have measured the voltage. How you would have measured the voltage? We will have a voltage per division knob, and then we'll count the number of squares it covers in the y-axis and the x-axis. So in the y-axis, the number of divisions covered with multiplied with the voltage per division will give you the exact peak-to-peak voltage of a signal. And if you have to measure the RMS voltage, then we have to multiply it with 0.707 and to get the RMS voltage. And as similarly, for a single cycle, you will normally measure the number of divisions along the x-axis and then multiply with times per division, and then it is recorded in your observation or record, and then it will be converted into frequency, right? And this is the exact usage of oscilloscope we have used in our laboratories. Okay, and this is the internal structure of a cathode ray oscilloscope, and we know that this cathode ray oscilloscope uses CRT, that is cathode ray tube, where an electron beam will be deflected by the horizontal and vertical plates depending upon the input signal, and uh, that will energize the fluorescent screen, and where we will see a uh, an illumination of that parts depending upon the input signal, and where we can measure it. Okay, we can see here this electron beam is reflected by the deflection coils. These we call this as a deflection coil. You will have two horizontal deflection and vertical deflection coils. Depending upon the input signal, these horizontal and vertical deflection coils will be energized. Based on that, that will be the light electron beam will fall on a fluorescent screen, or it is a phosphorescent screen where it will illuminate the screen depending upon your input signal. This is how very briefly the CRT or CRO works. Okay. And what the CRO can do, this CRO can measure voltage, time. From the time we can calculate the frequency, and also this CRO can also be used to measure the component. We can see, if you see the CRO front panel, there will be a 2 points where we can connect a component. Based on the signal that is available across that component, we can measure or we can test whether the component is working fine or not. So we can use this CRO not only for visualizing or viewing the electrical signals, also we can use it for component testing. And this CRO has a higher bandwidth and it has a high writing speed. And this CRO, it reproduces the signal into in an optical display at a more or less in a real time. Okay, there will be no much delay, or there will be no measurable delay between the input to the CRO and output display. Okay, and also this has a writing speed because the signals are not processed and the signals are used for only the deflection of the coils, and there is no much time wasted or much time utilized to process that signal. So we will get a highly real-time signal in a CRO. That is the one of the advantage of a CRO, using a CRO, and it has a larger bandwidth since we are using unlocked devices. So this will have a larger bandwidth, and it is comparable. It is highly higher bandwidth and comparable to the bandwidth that can be afforded by a DSL. Okay. And what this CRO can't do is it cannot do any storage, right? If you are doing any measuring a signal, we cannot store that signal because this is fully an analog device. The CRO is an analog device where there is no provision for storage because we don't digitize or store it any memory, or no memory is present inside that CRO. Will not be able to do any storage, and also the measurement has to be done manually, and it is not displayed in a screen or so. It is done manually, and we have to count the number of divisions along x and y axis. It has to be multiplied with the factor by multiplying it with the wholes per division or times per division scale. Okay, and if this CRO can't do any analysis. If you want to do some analysis, we have to store the signal and then we have to do analysis. Since there is no storing, the analysis of signal is not possible. So and eventually it doesn't assist any printing, right? So printing also need digitizing of the signals. No digitization, no printing. We cannot interface the CRO to computer or any other devices. It cannot be. We can only visualize the signal, or it cannot be interfaced to any other devices. And also we cannot manipulate the signal, or we cannot perform any mathematical operations on the signal. Okay, so we will get whatever it is as it is, right? So we will not be able to do any manipulation. We cannot do any mathematical operations on the signal. For a good example, if you want to find the Fourier transform, or if you want to view the spectrum of a signal, it is good to take a fast Fourier transform of the signal. Since it doesn't support any mathematical operation, we will not be able to take the fast Fourier transform of a signal, or we will not be able to multiply, add, or we can't do any math on the signal. We could see vis a vis. We can see whatever the signal that is available can be displayed at that moment, that can be measured manually. Okay, and also the CRO cannot uh, uh, we will not be able to acquire small variations, or a spike in a circuit, or whether if there is any malfunctioning in the circuit that happens for a moment, that cannot be measured or that cannot be stored, and this cannot be done on a CRO. But the advantage with the CRO is it gives you a real-time signal, and also it gives a fast writing. That is, it's very highly real-time. Okay, the delay between the input and output is it's unmeasurable, or if you even try to measure it, that would be a big impact on the signal, and then we will not be that and we can be see the signal in the real time. That is a real advantage, and also we will not be able to store the signal, and until we store, we can't do any math on it, or we cannot do any calculation on it. So therefore other like automatic measurement, analysis, printing, that it doesn't support anything. But the digital oscilloscope is like we can store. We can, from the word itself we can find it is a digital storage oscilloscope. So this oscilloscope, what it does is it digitizes the input signal, then it will reproduces in a, or then it will be displayed in the screen. And this digital storage oscilloscope, all the analog signals are converted to digital, then it's stored in some location, then it is buffered to a display. It could be an LCD display or LED display. That depends upon the device we opt for. We can have either a LCD display, and the latest devices comes with LED displays also. We'll get a computer like display to visualize the signal. And also this signal, not only we can visually see it, we can also numerically interpret it. Since we are storing, we can do calculations by, it is like a small computer. It can also calculate the time period, it can calculate the rise time, fall time, it can calculate the duty cycle, it can calculate the peak to peak voltage, it can calculate the RMS voltage, whatever the voltage and the time measurement it can do where we need it, it can be done all with the help of this digital storage oscilloscope. And this oscilloscope is very useful when we test, verify, and debug the electronic circuits. Okay, so especially when we have a circuit like SMPS, there may be sometimes a spike may come out. But with a high speed ADC and the number of frames it can create, or number of depending upon the speed of ADC, this digital storage oscilloscope can record these glitches in the circuit, or glitches in the current or voltage that has been generated in the electronic circuit, so that we can the debugging of this circuit can be done with the help of this from the output of this digital storage oscilloscope. But we have to keep in mind that this DSOs will not provide live data. There will be a distinctive delay between the input signal and the output signal displayed. Okay, and this speed of display depends upon the update rate of the digital storage oscilloscope, how fast it can convert and uh, uh, how fast it can display it on the, that depends upon the update rate of the storage oscilloscope. And this is the oscilloscope what we have in our laboratory, DSO X2002A. We have a 2-channel digital storage oscilloscope where you can see both the digital signals that you can see here. We have a digital IO pins here that can be connected, and these are the unlock channels what we do, right? What we can connect. This is two. We have two unlock channels, like how we have a BNC connector in the CRO. There are two connectors where we can connect the signal, connect the input signal, right? And also it have a 2-channel. All these done with the soft buttons. It all software control, and it can automatically do measurements. Now we can choose an unlock channel, and here we can see multiple digital channels are utilized to for the debugging of a circuit. So why we go for DSO for a DSO in a communication lab is we are going to visualize, or we are going to measure very complex signals when compared to all the laboratories we have done in our previous semesters. We're going to, even if you have to visualize an amplitude modulation signal, or if you have to visualize a sampling signal or any other modulated signal, it is going to be a combination of multiple frequency components. If it is a single component like what we have done in our electronic circuits lab or so, you are going to give a single frequency as an input, and you're going to observe the single frequency as the output. So where the measurement is going to be very easy, right? But here we are going to visualize the or we are going to measure complex signals, which signals are going to be function of multiple frequency components. And that frequency components, we can even measure it with the CRO. But when we use DSO, the measurement procedure or measurement gets very easier. Okay, so that's why we go for the DSO. Okay, and this DSO, what we have in our laboratory is a 70 megahertz DSO, where it can measure the signal up to 70 megahertz, right? And this DSO has a capability to store the signal. We can do analysis on the signal. We can do automatic measurements of the signal. And these all things can be done with the signal. We will see it by one. Okay. And also, this DSO can be interfaced to a computer, even if you are in your class, even if you are in your home, if your device is connected to a wire network, network, then we can measure the signals from your home also. Okay, so that is a bigger task, right? We can even connect it to a computer remotely. We can connect it to a computer, and then we can analyze the signal from our home, or even I can connect this DSO with the computer. I can visualize from my laptop or personal computer. And this DSO X2002A is a 70 megahertz oscilloscope, and it consists of two unlocked channels. And this can be viewed in an 8.5-inch WVGA display. We have a video graphics array. We have a video graphics array display, and in that the signals will be displayed. And this oscilloscope, what we have in our laboratory, can store 1 mega points memory. You can store up to 1 mega points of memory for a display, and also it can capture 2 lakh waveforms per second. It can update at a rate of 200 waveforms per second. So you just visualize how many number of waveforms can be registered in a second, and it is a very fast, one of the fastest available oscilloscope, digital storage oscilloscope in the market. And this gives you the front panel display of a of an oscilloscope. Here what we have in our image is a 4-channel oscilloscope, but here in our laboratory we have a 2-channel. Only we have a channel 1 and channel 2. We have channel 1 and channel 2. Other channels are not available in our laboratory. We have only 2 channels. And for the 2 channels, we have 2 controls. One is vertical control and another one is the horizontal control. Vertical control in the sense it controls the amplitude measurement, and by horizontal control in the sense we have a we can see that the horizontal control in the sense it controls the time divisions, right? Time divisions and frequency, how we do times per division and volts per division in the uh, uh, oscilloscope. Here we have a horizontal control section and vertical control section respectively. Vertical control section which controls along the y-axis, and a horizontal control section controls along the time axis. And vertical is along the voltage axis, and the horizontal section is along the time axis. Okay, and we have a trigger circuitry. We can control the triggering, or if we don't need to trigger at a certain time, unless you know when to trigger and where to trigger. Normally we don't work with in the laboratory. If you design a circuit, you want to trigger that outputs and all, so we can use this trigger circuit for that, trigger section for that. But normally in laboratory it is not required. We will make it as a, it will automatically detect the trigger voltages, and it will accordingly generate the signal at the display. Okay, and then we can see that there are 4 pins. One is a serial, digital, math, and reference. So here this serial digital means it is used to measure the digital signal, and then that is math, where we can perform mathematical operations on the input signal. Okay, so these are the and we have whenever any option is selected here, you'll have a soft switches, 6 soft, we call this as soft switches, like a menu button, where we will have multiple options here, where we can select the options. We'll be seeing it one by one when we have a real-time demo on the uh, system. Okay, so now and this channels, we have 2 channels in our laboratory. So we have we have to select which channel to display, right? We can parallelly select channel 1 and channel 2. If both are selected, it will act as a dual channel oscilloscope, right? So if you have a 4 channel in your laboratory, we have MSOs with 4 channel in our laboratory. We can measure 4 signals parallelly, and that 4 channels has to be selected. We have a visual display for that, and these lights will glow at 1, 2, 3, 4. If light glows, it means that channel 1 is on, 2 is on, 3 on, 4 on, depends upon it. Okay, and also this push, there is this buttons, not only it is a potentiometric buttons, you'll have a push button at the center that will push for, if you push the larger potentiometer, that means that it can do fine push. If you push and then if you tune, it is for fine tuning of the vertical section. And if you push this button at the center, it will push to the, push means it is pushed to the ground level. Normally what we'll do is when we in the CR, we will have a button where we'll push it, and it will stay 0 voltage, and you have to tune it for the ground level. Here it will, if you push it, it will automatically detect the ground voltage and it will move accordingly. Okay, and horizontal, we can have a horizontal times per division variation with the help of this larger potentiometer, what we or the larger tuning potentiometer what we have here. And this is for vertical movement, this is for horizontal movement of the signals. We use this smaller potentiometer, okay, and we can navigate with the help of this navigate button to move the signals, or we can either we can in real time we can see the signals, or we can stop the signal and then we can study the signal. And these are all possible with the help of this uh, uh, MSO, okay. And what this MSO can basically do is it can do peak to peak measurements. It can measure the peak to peak voltage, and it can measure the RMS voltage, and it can measure the rise time. So it can also direct the fall time, and it can measure the pulse width. It can measure the duty cycle. It can automatically detect the period, and if period is automatically detected, it can calculate the frequency of the signal. We don't need to have any manual calculations to do that. You select appropriate button, and you can see these all the things are displayed at the uh, all the things are displayed at the this bar, okay. So you have your 4 channels are selected here, and you will have the display in the side where you can parallelly show the voltage measured, time measured, and the frequency measured, okay, in this place, okay. And also it can perform some mathematical operations on the input signal. It can perform Fourier transform. If we can perform Fourier transform, we can see the spectrum of the signal. Normally we do analysis by using the spectrum of the signal. Even in your communication system or digital communication systems, we will do the Fourier analysis, or we will do the spectral analysis. That spectral analysis can be done with the help of this Fourier transform mathematical function that is available in that digital storage oscilloscope. We can measure the absolute value, that is the magnitude of the signal. We can integrate the signal. We can do addition, subtraction for on the whatever the input signals. We can add 2 signals, channel 1 and channel 2. We can add if it is required. We can subtract the 2 signals. These kind of mathematical operations can be performed with the DSO. And this is the probe that we are going to use in the laboratory. And this is the probe that is available. You can see here. So this is the probe that is available that is available with the laboratory, which is going to be connected to the DSO. And this will be connected to the ground line. We have a crocodile clip. This crocodile clip will be connected to the ground line, and this is the pin where we are going to connect it. Just pull it out and we can connect it. uh, we can connect it to as the testing points. Then we can do the measurement of the signal, okay. And now what we